It's actually really exciting that there's so many people who are brave enough to come to a talk on the notoriously complex topic of quantum computing. And I should give you a disclaimer at the start of the talk. I am actually going to really try hard to actually tell you today as much as I can about how quantum computers actually work, like why they're powerful. And the reason for that is, over the past 1 or 2 years, there's been an awful lot of articles written about quantum computing. And in fact, every month it seems like there's almost exponentially more and more written, and there's more in the media. But for good reason, a lot of articles tend to steer clear of actually trying to explain what a quantum computer is. And instead they focus on what we might be able to do with one if we have one, to varying degrees of success. And that's brilliant, and it's a good thing to do because we have good reason to believe a quantum computer would actually be really world-changing. And now is a good time because it's finally coming out of the labs and into big companies like Google, Intel, Microsoft, who are all actually trying to build one of these things, finally. But I just wanted to try and go a little bit further, give a bit more of an in-depth idea today. So you've been warned. This actually, I don't know if I should say this might be the most complex content I've ever put in a talk, but I'm going to try and go through it really slowly. And if at any point you're fed up, just tell me. I love heckling. Like seriously, just tell me. We'll figure out. I'd rather you got one thing out of this that you really got your head round than I just sit here and feel good about putting picture after a picture after a picture. So, that's what we're going to talk about. And that's why I've called this talk Quantum Computing for the Curious. Because I'm going to rely on some curiosity on your part to come along on this journey. I could have called it Quantum Computing for the Nerds, because I'm going to rely on you all being a bit nerdy. And if you don't think you're nerdy, I'm sorry, but you're at a talk about quantum computing, so just have to let you know that. And that's great, because you should be proud of being a nerd. Being a nerd's fantastic. And that's what we're going to do. We're going to try and understand how quantum computing works. I actually, at the last minute, changed this picture. I had a picture here before of a big cryostat that Google uses, but I changed it to a picture of D-Wave's chip. And that was just because I kind of realised a lot of you may have heard of D-Wave. You may have heard that they built a quantum computer. And I'm not going to talk about a device like D-Wave has. So this is instantly more technical than I would have already said at the start, but I just want to have another disclaimer. So D-Wave, a lot of people say they built a quantum computer. They didn't. They built a certain machine called a quantum annealing machine. And they're not sort of trying to pull the wool over anyone's eyes, they fully admit that. And it isn't the kind of device I'm going to talk about today, because it can only solve certain kinds of problems. And it's good at that, and that's great, and that's a useful thing, but I'm going to talk about a quantum computer that is more universal than that, which still has not been built yet. Okay, just to clear that at the start. So, if we want to understand quantum computing, how can we possibly do that? I'm a big fan of, if you find something new that's kind of strange, trying to understand it in terms of something that you already know. And so to do that, to help us kind of take that approach, I'm going to start off by recapping how a conventional computer works, and try and go from there to find the difference in quantum computers. Now, just to be clear, because I will use that term throughout the talk, conventional computer, so it's important to clarify. I mean by conventional computer, the kind of computer that we've all had for many, many years. This was my first computer. It made really cool noises, but it took about 20 minutes to load a game, so we've come a long way since then. I don't understand this, right? This is me in the UK, and I only noticed this when I looked at this photo for this talk. I've got like loads of what in the UK we would call American football, right? I have no idea that was what my wallpaper was as a kid, but I guess it's kind of fitting because now I'm American. Okay, so what we're going to talk about is conventional computers first to set us up, just in case. I mean, I know I'm in Palo Alto, right? I'm sure you're all mining Bitcoin with botnets right now on your phones as I talk, but just in case anyone needs to be kept up to speed, how do we talk to conventional computers, right? By that I mean, how do you program a conventional computer? Well, when you talk about coding on a computer, you normally think of something like this. I mean, text isn't important, but you think of someone typing this kind of stuff into a computer. And this is what we would call human readable code. Because a person could read it, even though it looks a bit like gibberish. It's got words in it, which is a good start. But a person could read it and write it. So it's just literally so the human can interface with the machine. But as soon as you try and run that code, an existing program on the computer, from the compiler, will turn that into something called machine code. Because as nice as this one is for us, a computer processor can't understand it. So we compile it into machine code, and this is really a simplified, just a set of only a few, relatively speaking, simple instructions that the computer processor can understand. So all of this complexity gets reduced down into sort of a combination of a few simple commands. They're super simple, things like move this information from here to there, or add, right? Just add numbers together. And that machine code is of course really just shorthand for what we all really think of as the language of computers, which is lots of binary. And lots of binary is also lots of instructions in a way. It's instructions to switch on or off one of billions of switches that the computer is ultimately made up of. So the computer hardware is really just lots of switches. And that is kind of amazing, but when you boil it down to a laptop or a phone, it's really billions of switches flicking on and off, right, all at the same time. I mean, quantum computers are weird, but I'm not really comfortable with this yet. Like, all the stuff you can do on a computer is just, and they don't make a noise, right, but they're just going on and off really fast. And of course, to make our lives easier, we use 0 and 1 to refer to the state of these switches. Normally we think 0 if the switch is off, 1 if it's on. I realise this just now as I'm talking, this is a UK light switch. I've just realised I've not seen any light switches that look like this since I've moved over here. So it's been a cultural exchange for you there. So this is what our computers are made of. They're made of switches. And we talk about bits when we say 0 and 1, which is really referring to a configuration of a switch in the computer. So, of course, you don't have switches like this. Really, they were switches with a switch on. You couldn't get your finger in. They're a bit too small now. And so what made computing possible was the invention of the electronic switch, a switch you can turn on or off with electrical current. This is from 1947. It's the first transistor. It was about 20 centimetres big, I think, something like that. We've got a bit better at making them smaller since then. And as Kay mentioned, you can see that really well in Moore's law, which says that every 2 years the transistor count, the number of transistors, electrical switches that we can fit on a chip of a given size is doubled. It's kind of crazy. This is on a logarithmic scale, if you know what that means, which is why it looks like a straight line. If you put up a normal graph, it goes really quickly. And I was not joking when I said billions. If you look, this is only back in 2016. We're already at the tens of billions already. So we have a lot of switches in modern computers. But despite this fact that this really is impossible, right? This is science fiction. The fact we can build these things is, in my opinion, the most amazing achievement humankind has ever made, that we can build so many things in such a small space. But despite that, as Kay alluded to, there are still problems that a conventional computer built on switches can't ever solve. So I'm about to do what I kind of criticised articles for doing, which is give you a very quick motivation for why we want a quantum computer, but only in a few slides, and then we'll explain what a quantum computer can do. So there are problems you can't solve with a conventional computer. This is the world's most powerful supercomputer, Harrigan. And this supercomputer spends a lot of its day trying to design drugs. So drug design is a very difficult problem. Basically what we're trying to do is simulate the physics of a molecule to understand how it will interact with other things you care about, like maybe part of the cell or some protein that's in your body. And those simulations are very difficult because the laws of physics you need to understand to do them are quite complex to solve. So Harrigan, despite being the best supercomputer in the world, it can only simulate a molecule with round about 30 atoms. Here's a molecule with round about 30 atoms, it's got 24. This is caffeine, possibly the most important drug in the world. And when it's kind of caffeine, I've modified it for the purposes of this little slide. But the problem is this: if this is the most that Harrigan can simulate, if you add just one more atom onto this molecule, then roughly speaking, you need twice the computing power. Add another one, you need 4 times. Add another one, you need 8 times. It will double and double. It goes up exponentially. And so you don't have to go very far before you're in trouble. This is TPA. This is a 100-atom molecule that's used, it's believed to be useful for curing or tackling cancers. But if you wanted to simulate this on Harrigan, if I remember my very, very rough back in the envelope calculation, I think you need 1,000 million, or maybe it's billion, but it's a lot, right? You need that many more times computing power. So it's not just that these problems are hard, they're like absolutely unachievably difficult. And those are some of the kinds of problems that a quantum computer can solve. We can't do it with a conventional one. You can't do it if your computer's made of switches, i.e. transistors. This is a more modern transistor made of silicon, or bits. If you're into that kind of game, those problems are probably out of reach for you. But what could you do, right? What could you possibly imagine a computer doing other than flicking switches? For about 60 years, it's all seriously considered a computer to do down at the bottom. Well, luckily for us, in the 80s, some physicists got really bored. Physicists tend to do that a lot, it turns out. And when they were bored, they thought, well, I wonder what would happen if we took some really small things, like atoms, that obey the strange laws of quantum physics, and just for fun, what would happen if we tried to use those as switches in a computer? And it turns out, you get really weird switches, and I've tried to represent that by putting loads of switches in. It's a very useful technical diagram. You get very strange switches, and you no longer deal with bits in your computer. Your bits are now quantum, so we call them qubits, because it means quantum bit. And if you build a quantum computer with qubits, it turns out you can start to solve some of those harder problems. And if you do that, of course, this whole kind of, if you like, stack will change, right? You can still write human-readable code, that's great. It's still easy to sort of program in a sense. But that human-readable code will compile down, so I should have drawn a different, I'll use the same picture, but I'm lazy. But it will compile down to a new set of instructions for your processor, because your processor now can do things it never could have before. So you have new quantum instructions, quantum machine code, if you like, and that will compile down ultimately to deal with your quantum switches, your qubits, rather than bits. And if you build a device like this, it's not only drug design that you can do much better, there are lots of problems a quantum computer will potentially help with. And I should be really clear though when I say this, there are some problems where the advantage you get is really significant. There are some where the advantage you get is pretty good, and there are some where you get zero. In fact, most things you would want to do with a computer, a quantum computer will be no better for you. That might not be surprising because the problems we use computers for now are problems that, from the very start we thought about doing because we knew a normal computer would be good at them. So that maybe isn't super surprising, but it's definitely, if people tell you quantum computers will change everything, then they aren't looking very far about what everything means. So what's probably going to happen, because of this fact that quantum computers are good at very specific problems, and by the end of this talk, if we have time, I might be able to sort of help you see how you would identify those problems. What will probably happen is this. Your normal computer, your conventional computer, will definitely still exist. It will definitely do everything. You'll still check Facebook on it, no quantum Facebook. And what will happen is whenever it comes across a problem that it knows a quantum computer would be good at, there'll be a special quantum processor in your computer, and it will send some information, some normal bits, specifying that problem. The quantum processor will be like, I've got this, I'm good at this. Mad stuff happens, and then it will send back an answer that the normal computer can understand. And very likely the first times this will happen, it won't even be that you have a little chip in your computer, it will be somewhere in a big lab or a big facility, and you will connect to it over the internet. Because these problems are so difficult that connecting over the internet is a very little overhead compared to the time it would take to solve the problem. So this is just for your information, what you can expect quantum computing to look like to begin with. I mean, I showed you that picture of the transistor, right? And you laugh at that now, but the point is, no one really knows what will happen, what we'll discover about quantum computing, how prevalent it will become. But if you wanted to sort of, say, take a gamble right now, my gamble would be that at least for a while, it will be like this. Okay. So I said at the start I was going to get hardcore and really technical and try and explain quantum computing to you, so you've had it easy so far. I hope that seemed easy. Let's do it, let's go through the proper explanation. So to understand why quantum computers can have this kind of a power, we really need a better description of qubits. I'm afraid that this several pictures of a light switch just isn't going to cut it if we want to really understand what's going on. And so I'm going to try and tell you in more detail how qubits work and why they're powerful. Now you kind of know what a qubit is and how it differs from, where it sits in the computer. But if I say to you that, I say I'm going to explain to you what a qubit is, probably your inclination is you think, oh good, I want to know what a qubit is, I want you to explain this to me. Like, what is this thing in the computer, right? If I looked at a quantum processor and zoomed in, what does a qubit look like? Is it an atom? Is it like a bit of light? What's it doing? What's the hardware look like? Because then you'll understand, right? Well, I'm not going to do that. I'm going to say no. I refuse to tell you. Or at least if we have time in the second part of the talk, I will tell you a little bit about that. But if you want to understand how a quantum computer works, this is a big distraction. So imagine I wanted to teach you about a normal computer, conventional computers. If I started telling you the physics of transistors and charge transport equations for MOSFETs, that would be a really big diversion where all I should really do is say, look, imagine you have something that can be 0 or 1. You can do all this cool stuff. So I won't talk about the physics hardware, because this has got a lot of quantum physics and stuff in it. I'm going to try and find something like zeros and ones, some rules of the game for a quantum computer, and show you how if you have a thing in your computer that obeys those rules, you get power. Then if we have time, or you're interested enough, I'll tell you what some of the things people try and put in those chips are that obey those rules. If that makes sense. Okay, so how do we describe a qubit? Well, in the conventional case, this is on normal bits. It's easy to describe a normal bit with 0 or 1. You get lucky, right? The hugely technical mathematical description of bits is just 0 or 1. It's like the simplest maths you could imagine. So you just learn that, and it's not that hard to get your head around, right? But if you want to try and do the same thing for qubits, things get a little bit more tricky. You see, a bit can only be in one of two states, so you just need 0 and 1. But a qubit can have many, many more possible values. I've just written 5 here, but there's actually infinitely many. And so a qubit doesn't just have 2 possible values, possible states it can be in, there are many more. And to make things worse, the mathematics gets really complicated. In fact, I didn't do you justice, this is not the most complex the maths can get, that I showed you in these examples. 2 of them look alright, and in fact these are kind of like the equivalent of if we had normal bits in a qubit, and I'll explain that a bit more in a minute, but all the other options get very complex. So what we need is a way to talk about qubits that unfortunately isn't going to be in the textbook mathematical way that lets us get our heads around things a bit more. And so I'm going to introduce for you a visualization, a graphical notation, a pictorial way to think about qubits that I think will let us actually begin to understand what they're doing, okay? The best way to introduce this is to do it first for bits and then extend it. And it's called circle notation, right? So it's not going to have equations, this talk, but it's going to have pictures. So maybe that will... Let's see. So what I'm going to do is this. I'm going to say circle notation works like this. For your bit to begin with, let's just do a normal conventional bit. You draw a circle for every possible value you could see that bit in. Everything you could read out the bit and find, you draw a circle for it. So for normal bits, that's easy. There's just, you look at a bit, you read it out, it's either 0 or 1. So I draw a circle for 0 and a circle for 1. And then all I do is something that's kind of a bit of overkill. I say, if my bit is in this state, if the switch is off, if it's in 0, I colour in the 0 circle. If the switch is 1, I colour in the 1. And that's how I would represent a normal bit in circle notation. Is that alright? Is that the problem with this, when you try and do this for a bit, you're like, why are you doing this? It's overkill. It makes it more complex, right? Just say 0 or 1, but it will be invaluable and indispensable when we try and apply the same idea to qubits. So let's do that. Let's see what a qubit looks like in circle notation. So the first thing we need to do, like before, is think what are the possible values a qubit can have when I read it out. And I said to you before, there's infinitely many states a qubit can be in. So you might think, you're going to have infinite circles, that's going to be great for them. But actually no, when you look at a qubit, when you read it out, you get an answer. Like a normal bit, it will only ever give you 0 or 1. So that makes our lives a little bit more easy to begin with. So in circle notation, for a qubit, we still only need to draw a circle for 0 and a circle for 1. Because whatever happens before we read out the answer, no matter how weird things get, and they do get weird, when you read it out, you're only ever going to see a 0 or 1. So there's some nice things about qubits. Okay, so that's what we're going to do. But the problem is, when we start seeing what states you can have before that, what the circles can do, it gets a bit weird. So you can just have 2 different states that are just like the normal bits. If you want, you can prepare a qubit so that only the 0 circle is coloured in, or only the 1 circle is coloured in, right? So this is kind of the qubit equivalent of just having a normal bit, a normal switch that can be on or off. If you built a quantum computer and somehow you built it so it was only ever allowed to make its qubits be in these two configurations, it would be the world's most expensive normal computer, right? And you would have wasted a lot of money. But we don't want to do that. We want to take advantage of all these other possibilities too. By the way, this is what the real mathematical description looks like. See these weird brackets? It's called bracket notation. I'm not going to use it, but I do leave it around my zeros and ones and numbers just to remind you that's a qubit that we're talking about, even though it can give you the same 0 and 1 as a normal bit. Okay? So what happens if we look at some of the other states? Well, things get messed. I'll look at state of this. So you can have, in circle notation, things that would never be possible with a conventional computer. Well, what does it mean that both circles are filled in a bit? Well, I mean, I didn't know if I just went like this, that was the end of the talk. That wasn't really good. But not only that, right, there's two things going on here that are new and different. The circles can both be filled in a bit, and also down here, you can see that I drew these blue lines, these dark blue lines, there to show that sometimes you can rotate one of the circles compared to the other one. Now, I know all I've really done is introduce these weird circles to you and told you some rules, right? What I'm going to try and do is show you, this is the best way to show you what the difference is. And if later on we have time, I'll tell you what you can physically do to a thing to make it become like this, so that the circle notation would look like this, okay? But to see the power of quantum computing and get some understanding, it's very useful. So there's two new things that we can do with a qubit. Our circles can spread across both possibilities, both things you might read out at the end, and one of them can rotate. So what does that all mean? Well, we give a name to these two different new parameters we have to cool. We call them superposition and relative phase. Super technical terms. This one's kind of too technical for me, but too technical I think to use, but I like this one. It's cool, right? So, what is superposition? This is in superposition. Relative phase, this has got its relative phase change. And these are the two new parameters we can tweak. When you have a normal bit, all you can ever do is flick it on or off. It's one thing you can do. Now we can mess around with the superposition of our qubit, we can mess around with the relative phase, and that's what will give us the power of a quantum computer. And so what I'm going to do for the main part of the rest of the talk, and if there's time, definitely some other stuff, is just try and explain to you what superposition is, why it's powerful, and then what relative phase is, which will quickly, but actually it turns out it's possibly more important, or as important. Okay, and all the time I do that, I'm never going to talk about these equations again, I'm just going to use circles. But you should know that every circle notation I draw down corresponds to a big nasty equation that you can use to really prove everything and is a proper fully mathematical description. So what is superposition? What does it mean if my two circles can be a little bit filled in each? Well, that's an interesting question. Recall that I told you that when you do look at the qubit, when you read it out, you only ever see 0 or 1. You don't see anything weird like this. So what would happen if I made a qubit somehow with some instruction that I use on my quantum processor, if I made it be in this state, what would happen if I read it out? But if you did that, is that a question? Yeah, go for it.
I just suggested about my time.
Go on, go for it, love it.
Maybe different probabilities of what you use.
It's very good for something like Monte Carlo simulation.
Well, so it's good. It is actually useful for Monte Carlo, but mainly because you can make random numbers.
Yes, exactly. So it's a good, very good random number generator.
Yeah, well, that is one thing. That's the simplest thing you could do. And if you use it as random number, all you do is you make that superposition we've had and just measure it. Because it turns out that the probabilities you get, 50-50, is like the physics says it's 50-50. It's definitely, no one can know. There's no way anyone could ever have known. That's the weird part of quantum physics, right? Is that the answer to your question?
Yes.
So that's the simplest
one is
the simplest quantum computer would just be put your qubits in at the start, and that's 0, nice normal 0. Put them all through HAD, measure them all, get loads of random bits. That would be the simplest way to do it. But it doesn't have the niceness of all the cancelling and the relative phase. And there was a question I...
Yes, you use the instruction that converts normal bit to qubit.
Yeah.
What's the instruction that manipulates the relative phase?
Oh, so you can have an instruction that's just called... what it's called is...
Repeat the question.
Yes, absolutely. The question was, I showed you that HAD is the name of an instruction that can create superposition. And I told you a bit about relative phase, but what is the instruction that can change the relative phase? And I mean, there's no real proper agreed upon names in a sense, but the quantum computing community just call it they just call it phase, right? An operation called phase. I mean, the question is, what is that? Like, what are you doing? What you need to know, right? What are your qubits? What physically in the computer is making the quantumness happen? There's one example that I like because I used to work with this. I'm not trying to dismiss any others, but here's one example of how you actually make a qubit, and it will help you see what phase kind of is, right? So one way you can make a qubit is using single photons of light. Remember in the quantum computer we were talking about 0 and 1 and superpositions and stuff. So what is my 0 and 1? Say I have two sort of ways that the photon can go. They're called waveguides. And the exciting thing is you can etch them into silicon, so you can make them in silicon chips. So you can have silicon chips with all these tiny little troughs that single photons will go along and you guide them along, right? And let's suppose the photon could go through the top wire, right? And let's say that's what we say by 0. Or the photon could go through the bottom line. So with two wires, we could use that to represent 0 or 1, which one it's in. And there's a really good way you can then make superposition. It turns out, and this is physics, right, but it turns out, so I'm not going to tell you why it turns out, if you send a photon, say initially in 0 in the top, and send it through something called an evanescent coupler, so basically the two different tracks come very close together, the quantuminess of the photon kind of leaks out into this one a little bit. So when it comes across and comes out, it ends up split between them. You get the superposition. So this would be how you would do HAD if your qubits were photons in two different waveguides. And phase, it turns out there's a way, there's several ways, it turns out there's a way you can do phase, which is that you put in one of the paths a little heater, so a resistive element, and it turns out that if you heat it up and you change the waveguide, you don't want to say slows down the photon if it was in that path, but it affects the way it moves through the material. And so when they go through, whoop, it will change the phase. Oh, I should have made that one. But that's how you could do phase. Now, if you have, say, superconducting qubits, which are another kind of qubit that people try and build, how you do phase might be different, right? Because that's how it works with photons. But there are other tiny weird things people can use. No one's decided yet what the best thing to use for qubits. Maybe it would be a combination of all of them, you don't know. Sorry, that was the world's longest answer.
Just a quick follow-on question. So the reason it's random when you read it out has to do with the quantum mechanics of it?
Yeah. So this is what my research, so I got too carried away with my research with the philosophy of quantum mechanics. Well, not too carried away, but it's awesome. So no one knows, right? No one knows why it's random. Which is, you hate it when people say that, oh, no one knows. So don't ask. Lots of people have tried to what they call complete quantum mechanics, which is to say quantum mechanics says it's random and it's weird. But is that really what's going on? Right? Maybe in 100 years we discover a new law of physics that if you look deeper in the atom, oh, there's like loads of cogs and it really made sense, it just looked random. There are good reasons why it's hard to do that, and people have proven theorems that show that if you try and do that completion, find determinism, predictability in the randomness, that you might find a theory that does it, but it will look like this, and this, and this, and these things the theory will look like are weird. Such as if things move faster than the speed of light, you don't ever want information to move faster than the speed of light, because you can then send things back in time, and then you're don't make me talk about bars, because also actually it turns out that does happen anyway. Sorry, okay. Another question. Nearly. Oh, sorry.
So my understanding of D-Wave, I just saw one presentation by them, but it would be superconducting because they use little tiny metal rods at 12 millikelvin. And they also use an annealing process, and apparently you have to represent your problem in some kind of a physical structure for it to work.
That's right.
Okay, so you said that is limited, but there's actually working computers around Los Alamos, places like that, and they're solving a lot of different problems in a very small problem space because they don't have enough qubits in it. But the question is, this is also limited. So why is D-Wave more limited than what you're talking about.
Right, no, I see what you mean. So I said that quantum computers generally, I should make that, thank you for asking, I should make that distinction clear in how that I've said all this. I said that quantum computers will only ever be good at solving, well, we only know that they're good at the moment at solving certain problems. So you can think of it like the quantum annealers that D-Wave build can only solve a very, very small set of those.
Okay, so this is the figures.
Yeah, so it's a question of universality, right? So the thing that makes modern computers incredible is that they're a Turing machine, so that software exists. So Alan Turing proved that, if you build this physical device, you don't have to build a different one to run Word, and a different one to run PowerPoint, and a different one to run Call of Duty or whatever. That makes me sound so old now. But the point is this, right? You can run software, the same physical thing, you can reconfigure, it's universal to run different things. So the kind of quantum computers I'm interested in, that I'm talking about, are universal quantum computers. And that means that anything a quantum computer could do, it can do. You can reprogram it and it can do it. The D-Wave machines cannot. They will solve one kind of problem. I say this, but this does not do them justice, but it's like a calculator versus a computer. That's a horrible thing to say, and I don't mean it as nastily as it might sound, but it's suited as far as we know to a certain kind of task. Useful tasks, we hope, but a certain kind.
So I know that IBM has created a 5-qubit computer that allow people to program on the cloud. They even said they have a 16-bit qubit computer, talking about a 56-qubit computer that they're making. What calculations have these things been used for? What have people actually calculated using those kinds of things?
So no quantum computer yet has ever done a calculation that could not have been done on a conventional computer. Right, so far, quantum computers have not been useful to us. And so that is a really important and really good question. And the question is, when, right? What do I need? How many qubits do I need to be useful? And there's a bit of a problem that, the whole conversation very much, it's easy to think the number of qubits because it's a nice number that you can look at getting bigger and bigger. But then you need to know more than just the number of qubits to know if it's useful. You need to know how long can you keep them for, how many things can you do to them before they die. So there's a lot of things you need other than just, if I just give you loads of qubits, it could be that it's also still not a great computer, right? But so assuming that we're just talking about number of qubits though, what people are interested in at the moment, and what people talk about, is something called quantum supremacy. And quantum supremacy is kind of a terrible name, but what it means is the first time a quantum computer does something, anything, that a conventional computer could not do. The caveat is, it doesn't need to be useful. It's still incredible, right? As soon as we do that, it's amazing, because it tells us that yes, the laws of physics allow it, right? It says something really interesting, but it doesn't necessarily have to be useful. And the reason people get excited about these 56-qubit computers and that kind of area is that it's believed that that's soon going to be the level at which you can do that. You can do a task a normal computer can't. But the tasks, what you end up doing, right, you can find tasks that you kind of construe to be easier to do with smaller numbers of qubits, just because, right? So the tasks that they talk about are kind of sampling from certain random distributions that you couldn't sample from that effectively with a normal computer. And no one knows, at least at the current time, that any of that is useful. It's just a proof of principle. So the question is, how many qubits do you need before you do something useful? And what will that be? That wasn't the question, I've made a question for you. Just make it go to questions, it's great. So the first thing a quantum computer is probably going to be usefully used for, assuming all goes to plan, is quantum simulation, which is the fact, like the drug design kind of stuff. Turns out that's something quantum computers are especially good at, because drugs, molecules, even new materials like the molecular structure, the equations I said were really difficult to solve for those things are quantum mechanical equations. So in a sense, you're almost saying to your quantum computer, it isn't quite like this because it's not as simple as, you don't literally like build the molecule in the computer, but you're almost saying, oh, I'm going to set up my computer to run as if it was that molecule, right? So the equations are similar, and see what the answer is. And that's why we call those applications quantum simulation instead of computation. That will probably be the first, I think, because quantum computers are so good at that. When 100 qubits is probably the easiest number to say that is kind of useful, but that doesn't mean we're halfway there, because you need 100 error-corrected qubits. So error correction is like hella hard. It's really hard in a quantum computer, right? Because the errors quantum qubits experience are different from normal kinds of errors. So quantum error correction is difficult. It turns out incredibly, so it's incredible you can error correct quantum computers, right? Because does anyone remember analog or heard of analog computing? It was touted as like a really big thing. One of the problems, as I understand it, I've never really studied it in detail, was the fact that in analog computing, you don't just have 0 and 1, you have everything between. So it's tempting to think that's like a quantum computer, it's nice. You don't have the relative phase, you don't translate the wrong answers or any of that. But the problem is that errors really mess you up now, right? Because an error can be almost anything. Digital computers have latching, which is like, the most incredible thing ever. You can have in your computer in a transistor a voltage that means 0, you think it is 0, and a voltage that means 1. And if you go away from 0, that's alright, as long as you don't go too far, I just go back to say, oh, that's 0. If I don't go too far, oh, that's 1. In analog computing, if you're saying, well, I'm going to put my information anywhere between so I get all the decimal places, well then like an error completely messes you up, you can't latch back, right? You're not where you're meant to be. So quantum computers, although they are not at all analog computers, in a way you could say the same thing. Well, this superposition, you can do anything you want. So an error needs to go a bit off, and you don't even know what you had. But incredibly, you can correct the errors in a quantum computer with just a few discrete steps. So that is a really amazing thing about quantum error correction, but it's still hard. And roughly speaking, you need tens of thousands, if not hundreds of thousands of normal qubits, or actual normal physical qubits, to make one logical qubit, so there's lots of redundancy, so that if you do some special stuff to all those qubits, you distill out from it one that's got no error, even though all those had error. And doing that means that realistically 1 million actual qubits is what people need. Well, I don't know that, but that's a good number to have in your head. 1 million physical qubits in order to achieve 100 error-corrected logical qubits is a good ballpark numbers. I'm not promising anything.
So, a couple questions, related questions. So when you're talking about like the drug discovery, when it's running the simulation, there's a lot of randomness going on.
Right.
And so the question is, when it comes back with the answer, does it come back with the same answer every time, or will it say, well, or run through a whole bunch of scenarios and say, well, these are the kind of probability distributions of the answers?
So
that's one. The other one similar is like, so for example, like a weather type prediction.
Okay.
Again, is it this, how deterministic is it? One, I guess, if you should get the same answer, and the other one is a probability matter.
So I'm going to effectively, and I hate to duck out with that question because I don't know enough about those applications. I know people do, and that maybe is like, maybe I shouldn't have talked about it at all because I don't know that much, but there are people who work in quantum algorithms, and quantum simulation specifically, and they know an awful lot. But so let me try and address, I think, the core of your question, and hopefully it does give you some kind of answer to. So how can, the fact you still have some randomness, how does that not still mess you up? Well, the answer is that you can sometimes engineer things, so you really are going to get an answer that means something, and it's very, very unlikely you get a wrong one. So you may be happy enough with that. The other thing is, maybe you run it more than once, right? Maybe you run it 5 times or 10 times and see what comes out most times. And maybe it's still more efficient to do that than to try the old way, right? So some quantum algorithms you might have to run them multiple times and sort of, from that get an answer. But the question is as well though, if you're simulating a quantum mechanical system and you want to see what happens, if you physically had the system and you measured it, which would be like, the amazing thing, then you're still going to be looking at a quantum thing. So for simulation, this is me wildly speculating, speculating. I don't know that it's what do you want your simulation to achieve because it's simulating a quantum thing anyway. I was totally scared of that question, right? I didn't give you a good answer, I'm sorry.
If you start with or go back to what you started with, there's a picture of a molecule.
You want to put it up?
Yeah, sure.
Okay. See if I can guess it. This one?
Yeah, so as a problem, I look at that and I think, look, every atom has an influence on every other atom. So that's where it starts to get complex, right?
Right.
It's sort of like factorial, isn't it?
You mean that the interactions are hard to model?
Or even that their possibilities are the number factorial.
So yes, well, do you want to finish your question?
Yeah, so if that's the case, then are there molecules or particular objectives that might lend themselves to a lower qubit?
Oh, okay, I see what you're saying. Yeah, so in a sense that's true, right? So there are certain configurations of matter that are easier to simulate because of the nature of them. The equation is described in the symbol, which is another way of saying they're easy to simulate. So there's something called the Ising model, which is like a model that you use to describe like maybe lots of different things, different like charged particles that are all lined up. That's not a great description, but certain materials, like magnetic materials, can be described that way. And so those things are perhaps easier to model. Quantum annealers, I believe, can do some stuff to do with Ising models as well. Like I say, it is really a different kind of thing. I haven't seen it at all. So you're correct. There are certain materials that have easier to describe. But they're not 50 qubits. Well, the useful things you could do with them are still not as far as we know, they're still not still not that low. But that is why quantum simulation might be best. Also because in quantum simulation, the error correction maybe isn't such a big deal, right? Because if you're simulating a quantum system, like a real material, it's noisy. Stuff comes in and messes it up. So maybe the noise in your quantum computer is useful in some sense to help simulate the noisy environment. In some sense. So there's a paper by the second research paper on quantum simulation suggests that you can use the noise in your quantum computer as a simulation of the environment. And again, like I'm not a quantum simulation person, right? So maybe that's an easy way out. You disagree? Oh, I was like, please tell me, please, if you know a way to do it. Let's talk. Start company. Right, okay. No, absolutely.
If you have these qubits and they don't take a lot of space, but they give you lots of data, lots of computation, how do you confirm all this? The fact that you came out with the same answer twice, that's nice.
Yeah.
But what's the utility of it? How do I confirm the utility of it?
Yeah, so that's a really good question. So how do you run a quantum simulation, right? Or you run an algorithm on your quantum computer, how do you verify that the answer you've got is correct? And the answer, I guess the best answer to that question is that you run it, so there are some problems that are verifiable, right? There are some problems where you can know you've done it, correctly, which makes you happy. So one thing that quantum computers are good at, for example, is, although I think this is not a good thing to focus on, and I'll say why, is like breaking cryptographic protocols, right? So, you can break RSA with sufficiently big quantum computer. RSA is the encryption system that the internet is, a lot of the internet is based on. So people love that because it sounds terrifying. I don't think it's as terrifying as it really sounds. In that problem, you've done it, right? You know you've done it when you crack that code, right? So you can know it's done faster because you just don't have the normal computer to do it any faster for you. But in other problems like simulation, that is an important problem. Like, how do you know your simulation is correct? And I think I don't, so again I've skirted and I don't know the answer. My quantum simulation knowledge is not good enough. I don't know what the current best ideas are for that. I have seen people like talking about that, but like I'm unfortunately going to let you down and not give you a concrete answer. So there are some problems where right, and they're great and they tell you your quantum computer's working, and to some extent I guess it's doing it, testing it, trusting it, but they're the sort of easy answers. I don't know the good stuff. Send me an email if you want, and I'll dig up the stuff I think I remember seeing. Someone else can tell you.
While that molecule is up on the screen, and back to medicines and people, there's a continuing effort to tailor and customize molecules for individual people and problems.
Yeah, right.
And quantum physics kind of understand the data of an individual human with the molecule and simulate reactions
Forward in time?
Yeah, so this is total hand-waving territory, right? This is like, what if territory. So it really is. But what you might imagine, kinds of problems we know they could be useful for that could lead to that is pattern matching, so searching through genomes, stuff like this. Those kind of search problems are very difficult, and a quantum computer can potentially speed those up. So you might be able to have that help you in that kind of respect. Another thing is, if you had a good enough quantum computer and you have the medical technology, maybe you can literally simulate the effect of like many different attempts at a drug on an individual's, own sort of genome or whatever it is, if it's like a genetic therapy, I don't know, right? But you can imagine that could be possible, but it is total hand-waving, absolutely. So yes, potentially, but potentially a lot of things. Yes.
Two questions, they're one kind of short. So one, for the energy requirements, so you kind of mentioned that, the capacity of a computer, you only need a couple of qubits.
Yeah.
How much actual energy does it take relative to say one of those
right.
computers to actually run a quantum computer? And then the other is, you seem to mention that basically the hard drives would not be a useful thing using qubits, given that you don't get the same state. So can you comment on both of those?
Yeah, so two really good questions. First about energy. So it depends how you build a quantum computer, the actual specific hardware. I didn't talk about it, but you can build qubits in different ways. But most attempts, not all, but most attempts to build a quantum computer need you to cool things down a lot. Because when things are warm, the environment is a little more noisy, things are bumping each other, etc., and it will ruin your quantumness. These things, qubits only act quantumly when you leave them alone. When you intervene, if you knock them in any way, it's as if you measured it, right? And the superposition tool goes away. So the fact you have to cool things down can be where a lot of the energy cost comes from. And so how much energy, I don't know, depends on the way you try and build them. But you're looking at like powering cryostats. So that's the kind of energy you're probably talking about. Interestingly, one of the problems that we hope quantum computing could help is energy, right? So, for example, the heart process that we use to make fertilizer, massively inefficient, yet we know that nature can do it very well. So all it is it's a materials problem, right? It's a sort of modelling of molecular modelling problem to find a better way to do that. So maybe I don't think they're going to be it's not well, they take energy, and that also hopefully will change. There's a lot of things that currently we need to cool down for. We might find better ways to do those at higher temperatures. Second question was about memory. So if I've interpreted your question correctly, one of the real things we don't have yet, or maybe don't even have a great idea for how to do, is quantum RAM. So you make this quantum state of superposition, and you're like, I don't want to read it out, right? I want to store it for a bit, and I'll get it back later. Well, if these qubits experience a lot of noise, and it's very hard to keep them isolated, that becomes a big problem, right? The coherence time is what we call it, how long before they stop being in this coherent superposition. So, generally speaking, most of the things people consider today as realistic, nearer-term applications of quantum computing do not assume a quantum memory, a QRAM. They just assume you do the computation as it all moves around, and by the end you get your answer, and then it can do whatever it wants. But a lot of the sort of applications in machine learning. So there's quantum algorithms that will be useful in machine learning and in solving systems of linear equations and stuff like this, and big data. And not many of those, some of those, implicitly rely on QRAM, which is why there's sort of a good reason to be sceptical about, well, not sceptical, but the proof is in the pudding. This is the problem with quantum computing, right? It's very easy for people to either totally malign it and say or for people to also say, yeah, whatever you want, it's brilliant, it's going to do everything. And the truth is probably somewhere in between as always, time will tell. I think I looked to someone today, but yeah.
You briefly mentioned that in order for qubits to be on superposition, they have to be coherent, they have to be quantumly connected in order to make these calculations.
Right, so something, I hope it's...
And that must be very, very difficult to get
right.
10 or 20 20 or 30 things.
Yeah. So this is something like, tell me if this isn't what you were really asking, if I just answer, because I have a question I want to answer on that, so I might not answer your question, but answer mine. So something I didn't talk about at all was interaction between qubits. I just talked about this one qubit. There are 3 of them, and we do different things to each one, but we don't talk about them at all. That's hugely important. If you imagine a normal conventional computer, if it was just a billion switches flicking off and on whenever they want, and this one never flicked dependent on this one ever, or any others, it would never do anything useful. So there needs to be interaction, and that is important, and it turns out in a quantum computer, you can do kinds of interactions with qubits that are way stronger than any normal interaction. I would love to tell you what I mean by that, but that's going to send me into philosophy mode. It's called entanglement. And it's believed that entanglement is needed for quantum computing. If you don't have it, you won't be able to build it. And you definitely need interaction. So yes, that is hard, and it's hard because I think you're hinting towards, if I've got my qubits over here, I've got to move this one over here to interact it, and then move it over maybe there again. So when I'm doing that, isn't that going to make loads of noise, and it's going to be hard to keep it? So there are ways around it. So one of the reasons I like photonic quantum computing is because photons are such high energy things that the environment doesn't hurt them that much, the quantumness of them. So even if a completely photonic quantum computer doesn't work, which I'm hopeful for, then one thing that might be useful is, maybe you end up having these atoms trapped here, and then you make the atom emit a photon, and now these things are entangled, the photon's quantumness and the atom, and then you send that photon through like a little guide because it doesn't get messed up too much, and then it hits this atom, and now this atom and this atom are entangled because they're linked. So it might be that by using several, there might be a mixture of technologies for that. So you could imagine a way that could work. But yeah, so interaction is important, it can be difficult, but it's fun. That was more of a pun than I intended. So yes, next question.
Trinity have an entangled particle on the satellite.
Right, yeah.
How do you know that information didn't travel faster than the speed of light?
Oh, thanks. I can't resist and I have to talk about it. So, the craziest thing in the world is if you entangle 2 things, this is what happens when you entangle 2 things, when you make them do this quantum interaction, right? Let me, let's imagine this bubble could be here, or it could be here. That's my 0 and 1, right? That's my 1, that's my qubit. If it's here, if it's there. And I put it in superposition. Ooh. No one knows what it looks like, right? Something weird. And then I'm going to make another qubit, and this qubit's going to be if my phone is over here somewhere, or if my phone is over here, right? And what I do is I throw my phone through here. So what happens? Well, if the bottle's over here, my phone ends up there. But if the bottle's over here, my phone, let's say, bounces back and it ends up here. So now the qubit for the phone is somehow linked to the weirdness of the qubit from the bottle. That's an awful explanation, but kind of gives you some idea about entanglement, because if they're linked, but in a way that is somehow related to the weirdness of superposition. There's not a technical explanation at all, right? But when you entangle things, you do a kind of weird interaction like that and move them away. What you can find is if you do a measurement on this one, you read out this one, and then you read out that one, they'll always agree. But what you could do is take one to the moon, right? Leave one on Earth, synchronise your clocks super well, and say you're like, right, 5 PM, we're both going to measure them. Exactly. You both measure and they agree. So you're like, oh, they agree, right? That's super weird. Or is it weird? Right? How could they possibly agree? There's 2 ways they could agree. One is, when you did that entanglement at the start, they sort of imagine they could talk, right? Like, what are you going to do? What are you going to do? Oh, I'm going to give a 1, okay? Oh, I'll give a 1 as well, let's do that. They have an agreement, a prior agreement, and they go off thinking this is going to be good. And why we can never use it. You can only ever tell that it worked when you come together and check your results. You have to walk together. So then, you didn't send anything faster than that because you had to walk together to check it. This is the most messed up thing about the world, right? This is super, super messed up. In the world, this definitely happens. Reality communicates faster than light. Or it does something that's as if it communicates faster than light, but in such a way that we can never use it. And therefore never send information back in time with weird stuff like that, right? What is going on? I don't know.
The answer is it did communicate faster.
I forgot your question. What was your question? Sorry, I got carried away. What was the exact? You asked if something specific.
The answer is that it did communicate faster than the speed of light.
Well, so the question is, the quantum information went faster than light, but any kind of like normal information we have access to didn't. So it's a hard answer, but it's a bit of both. Well, not a bit of both. It depends what you mean by information. The devil in that detail is what kind of information. But that is like the question. That's great.
Hi. So the way I understand it, the number of quantum in the quantum computers gives you a certain amount of computing space. Right? That's one dimension. Now the other dimension is the number of possible multiple states you can have in one quantum computer. Right? So you gave an example of 5, so you mentioned it was any other.
Just say that bit again. You mentioned.
You said it was. I think in your example you showed like 5 or 6, but it's unlimited. I think is what you said. It could have many states. Sorry, I see exactly what you're asking. Right. So isn't that another dimension of increasing the capability of quantum computing?
So that's. I think that I see what you're asking. I think I made it confusing when I explained it, but I get what you. Let me see if I can explain. So, I said when I showed you the superposition, right? That what gives you these infinite possibilities? What gives you these infinite possibilities or infinite number of states is the fact that so I can vary continuously. Like exactly how much choice, how big is this area compared to that? I can keep going to more decimal places, but that isn't the useful part in a sense. In the same way, so that isn't. So basically, this is this is one of the weird things to get your head around in quantum computing, is that you have many options like that. But your computational power is still bounded. So there's a straight answer to your question that isn't going to make things more confused because I'm not going to explain it very well. Is that yes, you only have a certain amount of computational power, which does depend on your qubits. So yeah, it's a good question, and I didn't make that very clear. That was definitely a good question.
So how the technology used will determine how many of those quantum patterns you can actually use. How
do you determine how many qubits?
In that proportionate area.
Yeah.
The proportionate area that you can divide them into is going to be determined by the technology used.
Only in the sense that how accurate your technology. So say I write a quantum algorithm, and then somehow in my algorithm, it's super important you get exactly a 70% chance of it, right? So yeah, the technology. Another important thing about the technology is how well can it prepare a given state. The state fidelity, so that is important. State preparation, the ability to prepare states, is one of the key things you need in a good quantum computer, and that's difficult too.
So I think we could all go on like this for hours, but I think we just have time for one more question. I saw that there was another one over there.
It seems to me that maybe one of the issues with quantum computing is that the answers that you get are fundamentally statistical. In other words, you get an answer, but you only know what the probability of that answer is, or maybe the computer simply chooses an answer or spits out an answer that is the most probable answer that is possible. Okay, could one consider maybe there's an issue of how to preserve that answer, especially if there's an introduction of a source of noise into the answer. So maybe one could consider maybe combining a quantum computer with a conventional computer, where the quantum computer basically feeds its best answer to a conventional computer for the purpose of preserving the most probable state of the answer, so that there's archiving of the answers that you most likely are likely to want.
So if you do that at any point during the computation, so you get halfway through and you're like, oh, I'm a little bit worried this is going to go awry, I'm going to back up my computation. You have two problems, right? The first is there's a principle in quantum computing and quantum mechanics, in fact. You cannot copy quantum information. So you can't, it's called, no, right, it's exactly right. It's so, great. And you can't clone the state of a qubit ever. You can't copy it. In fact, one of the first proposed quantum technology applications way back, maybe before the 80s, I'm not sure, was quantum money, because you can't copy you certain number of qubit states, like represents your banknote, you can't copy it, you can't, it's forgery proof, right? So you can't ever make another qubit be exactly like yours if you don't know what it is, and if you do know what it is, you've measured it and you've got the proof or something. So you can't just copy it, keep backups, let it go off, I'll try again. So it's called the no cloning theorem. So that doesn't let you do that. But your suggestion of storing in a conventional one, well, that's when you hit this problem, right? Like I gave you that graph that showed a conventional description of a qubit and then what a qubit can do goes up to 112 qubits, the size of the Earth in a conventional memory. So you just physically can't write it down. You can't write down that description well enough to back it up. And even if you could, at some point in your computation, things are going to be in some way random. How do you can't measure it, you have to measure it many times to get a better and better idea of that. So there's many reasons that it has to stay quantum. But yeah, that would be that would be what would be worth trying. Right? But it turns out you get scuppered, unfortunately. Good question, really good question. Okay.
Thank you so much, Nicholas. Thank you.
No problem.